Yellow Rabbit Mathematics. Today's topic is going to be an introduction to derivatives. At its basic core, a derivative is nothing more than an infinitesimal change in a function. This seems a little bit abstract to start out with, however, so let's start by looking at derivatives graphically. So let's start by considering the following function. F of x equals x squared. So as I'm sure you've seen before, the plot of this function looks more or less like this. And I'm just going to label a couple of the important points. Here we've got 0, 0. And then I'll label here the point 1, 1, 2, 4, and 3, 9. So here's our plot of the function x squared. Now we can approximate the slope, or the rate of change, between any points along this curve using a simple formula. Let me write it up here. So the slope between any 2 points is simply equal to the change in the output of the function. We can call this delta f of x, divided by the change in the value of x. We can call this delta x. So let's say, for instance, we were interested in approximating the slope between the points 0, 0 and 2, 4. So that would be essentially finding the slope of this line here. Our outcome would be slope equals change in the output of the function, 4 minus 0, divided by the change in x, 2 minus 0, to give us a result of 2. So this would be the rate of change, or the slope, between these 2 points. But let's say instead of the slope between 2 points, we want the instantaneous rate of change. So we want the slope at one specific point. For instance, let's say we want the slope exactly here at the point 1, 1. If I try to use the original equation, I'll quickly run into a problem. So the change in the function, there is no change, we're at a single point. So it would just be 1 minus 1, divided by the change in x. Again, it's the same point, so 1 minus 1. I would get 0 over 0. It doesn't work. So we need a different method in order to solve for the slope at this one particular point. The method we're going to use is to start by taking a small change in the function right around the point of interest. So let's say a very small change around the point 1, 1. We can call this small change delta x. And then shrinking that change towards 0. What this does is basically allow us to find the slope between points that are getting increasingly close together. In the most general form, this would look like finding the slope between one point, x comma f of x, and a second point, x plus delta x, that small change, comma, f of x plus delta x, again that small change. If I plug these points into my slope equation, I'll get the following result. Slope equals change in f of x again over change in x. So here that would be change in f of x is f of x plus delta x minus f of x divided by x plus delta x minus x. I can't simplify this expression very much at the start, but I can here see that my x minus x in the denominator will cancel, leaving behind just the delta x. So here we go with our starting point. Let's now simplify this expression using our function of interest, x squared. So if I plug in f of x equals x squared, then my next quantity, f of x plus delta x, will become x plus delta x squared, or x squared plus 2x delta x plus delta x squared. Alright, so let's go back and substitute these into our slope equation. We now get slope equals x squared plus 2x delta x plus delta x squared minus the original f of x, which is simply x squared, all divided by delta x. What simplifies down here? Well, first of all, I can cancel the x squared and minus x squared in the numerator. And now I can divide out by the delta x to get a final result of 2x plus delta x. Now remember, however, our goal is to shrink the value of delta x towards 0. So delta x should be going towards 0. As delta x goes to 0, what happens to our expression for the slope? The slope goes to 2x. So what have we shown by doing this? We've shown that an infinitesimal change in the function x squared with respect to x is equal to 2x. This is the derivative, so we've solved for the derivative using this graphical method. We can write this as derivative with respect to x of the function x squared is equal to 2x. Another way to think about derivatives is as an instantaneous rate of change, or as the slope of the line tangent to the curve. So the line tangent to the curve is the straight line that just barely touches the curve at the point of interest. So for instance, for our graph here, if I'm looking at the point 1, 1, the line tangent to the curve of x squared at 1, 1 would look more or less like this. So the derivative at this particular point is just the slope of the line drawn here. I can solve that value using my result. So at the point 1, 1, the derivative is equal to 2 times the value of x, 2 times 1, which gives me a result of 2. Now let's do another practice problem to test this method again. Let's start with the function f of x equals x squared plus x. And let's find the derivative for this function. So recall from before that if I want to find the instantaneous rate of change, or the slope of that line tangent to the curve, it's simply going to be f of x plus a small change minus f of x divided by that small change. So to get started, I need these quantities to plug in. So I already have the formula for f of x written here. What about f of x plus delta x, that small change? This will give me x plus delta x squared plus x plus delta x. If I expand this out, I get the expression x squared plus 2x delta x plus the quantity delta x squared plus x plus delta x. And unfortunately, there's not much I can simplify down at the moment, but let's start plugging into our instantaneous slope and see what we can do. So here now, plugging in for my expressions, I get x squared plus 2x delta x plus delta x squared plus x plus delta x minus the quantity x squared plus x, so minus x squared minus x, whole expression divided by delta x. Now let's start simplifying. First of all, we can cancel out this x squared minus x squared. So those terms are gone. Next, we can cancel out this plus x and minus x. Those terms are gone. And now we can divide everything through by delta x. This gives us a result of 2x plus delta x plus 1. Now again, remember, we're taking the limit here as delta x, infinitesimal change, goes to 0. So in this case, as delta x goes to 0, this instantaneous slope will go to 2x plus 1. So what have we done here? We've solved, and we've found that the derivative of x squared plus x with respect to x is equal to 2x plus 1. Now, this method for solving derivatives is a little bit tedious, a little bit lengthy, but fortunately for us, there are some simple rules that derivatives follow. So if you check the supplemental information for this video, you can see a document with some general rules of derivation, as well as some common derivatives. If you familiarize yourself with this material, taking derivatives will be very simple and very straightforward. Thank you for watching this Yellow Rabbit Mathematics video. I'll see you next time.